Let's continue with further investigation. So at this point, we have our audio as a NumPy array. So either we recorded by ourselves or we uploaded. This time, just to demonstrate, I'm going to upload. It's the same audio I recorded the previous time, but I just saved into a file, and now I'm going to upload. So I'll choose here. This is my file, hand sound. It's uploading. It's 100% done. Extracting audio features. Here we can play it back. So it saved the hand sound as head sound 1 because I had previously already uploaded, but I didn't record for the tutorial. Now it's calculating the features using this DDSP training matrix compute audio features. We are going to take a look at this in the next tutorial. In this tutorial, we are going to see how they are plotting this spectrogram and how they are playing back audio. So now here we have our spectrogram. So we have time on this x-axis and frequency on the y-axis. Here we have the plots of the features. This is not the topic of our tutorial today. This we will take a look in the next tutorial. So this time the audio features took 37.1 seconds to be extracted, and we can listen to the uploaded audio file. So it's the same what we've been using so far. And now let's take a look at the spec plot. So I will include a code cell here. Let's see, spec plot. So this is from the DDSP training plotting.py. We have this spec plot. I have some arguments. It takes the audio, and we have V minimum and V max, rotate through. So this probably is to rotate, to change the X and Y axis. A size, so here the size is typically 512 plus 256. We need to plot the log magnitude spectrogram of audio. If patch, take the first element. So this is what it's doing here. If the length of audio shape is equals to 2, audio is equal to audio 0. And here it will have the log magnitude. And to compute this log magnitude, it's using spectral operations compute log mag. So this is what we need to look. So here we go to the github.com/magenta/DDSP. Let's go to DDSP. Let's go to training. Let's go here to plotting. And here is the plotting utilities for the DDSP library, useful in Colab and elsewhere. And here they are importing from DDSP, they importing spectral operations. And here the first one is the spec plot, what we've seen before. So let's go back there. Let's import the spectral operations. Now let's spectral compute log mag. And here we have the spectral ops compute log mag return the safe log of compute mag audio, and the arguments are audio, size, overlap, and bad end. So this is on the spectral ops, and inside the spectral ops it uses also this compute mag. So first it computes the magnitude and then it takes the safe log. So let's see compute mag. And the compute magnitude is using TF, so TensorFlow absolute value. Here is computing the short time Fourier transform, then is returning the TensorFlow Float32 version of this magnitude. So we need to take a look what is this STFT. So it's a short time Fourier transform, and we have the differentiable short time Fourier transform in TensorFlow computed in batch. So what it's doing is first is computing the short time Fourier transform, then is taking the magnitude, then is take the safe logarithm of this magnitude, and then we have the log mac. So the STFT, we remove the channel dimension if present. Here we have the TF signal short time Fourier transform, and we have the frame length, the frame step, the FFT length, the padding, and we can also take a look at the TensorFlow signal short time Fourier transform. And here it is part of the TensorFlow signal spectral operations and computes the short time Fourier transform of signals implemented with a GPU or TPU capability and supports gradients. So they did here Fourier short time Fourier transform algorithm using TensorFlow operations, so it can be used with GPUs and it supports gradients. So we see that it's everything interconnected. So the DDSP library is based on TensorFlow, and it will use TensorFlow operations to build these DSP blocks. So we've seen it uses the TensorFlow signal short time Fourier transform, then it will have this DDSP spectral operations. We can also take a look at the safe log. Oh, it's not made a mistake here. So avoiding the taking the log of a non-positive number, what makes it safe. So TF where x is smaller or equal to this epsilon, and epsilon is defined as 1 to the power of 10 to the power minus 5, and it will calculate the logarithm of this safe. So it will replace all the negative numbers by this epsilon. By default is 1e to the minus 5, and then it will take the logarithm. So we've seen the specplot uses the log mag, that uses compute mag, that uses short time Fourier transform, that uses the TensorFlow signal short time Fourier transform. So if you're not familiar with short time Fourier transform and you want to learn more about it, I encourage you that you go to Guitars AI YouTube channel and Guitars AI GitHub. There you'll find many different tutorials. Especially there is the advanced digital signal processing. It's offered by Professor Schuller at the University of Technology, and also the multi-rate signal processing, and there we explain more about this time frequency representations and about the short time Fourier transform, and also about the Fourier transform and the fast Fourier transform. So all these concepts that they are basic into the digital signal processing. There are some tutorials available, but have in mind that these tutorials, especially the ones from the University of Technology, they are targeted to master's degree students. So there should be already a knowledge of this basic signal processing techniques from the bachelor's degree, but still is possible to refresh or to catch on. But let's move forward. So we already know how to plot with the spec plot. Let's just take a look once more. Spec plot. After it gets the log magnitude spectrogram, it will rotate if it's the rotate is true, and be rotating 90, and then use Pyplot Matshow. It will take this log mag and it will plot using this Matshow. And here we have just taking some ticks, having the X label and Y label, and we have this plot here, so they don't show any values in the axis, but yeah, it's not really useful if you don't know much about this plot. You don't know what the frequencies are or what the time is, but still, just to visualize the audio that we uploaded or recorded. We can also take a look, if you're not familiar with Numpy Rotate 90. Let's take a look what it's doing. So it rotates an array by 90 degrees in the plane specified by axis. Rotation direction is from the first towards the second axis. So it returns a rotated view of an array. It's an array of 2 or more dimensions. Now here's one example. We have this M, it's an array 1, 2, 3, 4 type integers. When you rotate this, you have 2, 4 and 1, 3. If you rotate in another axis, then we will have 4, 3 and 2, 1. So you can rotate many forms. You can define the number of times the array is rotated by 90 degrees, and also the axis. So the array is rotated in the plane defined by the axis, and the axis must be different. So this is what rotate is doing. Let's close all this help that we investigated here. Let's go back to the spec plot to see if we are missing something. Spec plot. So we've seen the compute log mag, we've seen the rotate. Let's take a look also in this Matshow. So let's go on Pyplot, in case you are also not familiar with this function. So display an array as a matrix in a new figure window. The origin is set at the upper left and corner. Rows are displayed horizontally. The aspect ratio of the figure window is that of the array, unless this would make an excessively short or narrow figure. So from a function from Pyplot, matplotlib, and it plots an array as a matrix. So I think we finished everything from the spec plot. We know how to plot, and now we have more information about this spectrogram. So before we just see maybe some frequencies, some time, but now we understand the default values. We need to look at the compute mag. Here we have some sizes, and also we understand that it's the log magnitude spectrogram. Now let's move to playing back this audio. So much probably they are wrapping around some HTML5 audio controls, and this is done by the play audio. So let's investigate what this play audio is doing. So play, it is a function from DDSP Colab Utils and creates an HTML5 audio widget to play a sound in Colab. And this function should only be called from a Colab notebook, so it will not work if you're not in a Colab notebook. As an argument, it takes an array of floats as a 1D or a 2D array-like container of float sound samples. The values outside the range of -1 and 1 will be clipped. It also needs a sample rate, so the sample rate in samples per second. There is this argument called ephemeral that if set to true, the widget will be ephemeral and disappear on reload, and it won't be counted against real-time document size. And there is autoplay that if it's true, it will automatically start playing the sound. Once again, if patched, it takes the first element. We've seen here this before. It is going to use this kind of normalizer they're calling here. So there will be this array of ints, and they are using this mem file. It's IO bytes IO, and they wavewrite this mem file. There is the sample rate and the array of ints. Here we have this audio HTML for audio control, the source control, so it's wave base 64, the base 64 wave file. If your browser does not support the audio element, it will display this message here. Then we have here once again the base 64 encode, so now it will encode to the base 64. First it will decode from ASCII, the mem file get value. It will close this mem file, and then for this part if it's ephemeral or if it's not ephemeral. There are also other ways to play this file. We could use IPython display audio, but they decided to go for this way here. So there are some things here. Let's see, for example, what this Numpy info is doing. So machine limits for integer types. I'm setting some machine limits for integer types. We also have here is IO bytes IO. So we need to import IO first. So it's a buffered IO implementation using an in-memory bytes buffer. Then we have this Wavfile write. It will write a Wavfile. So this Wavfile here is from Scipy IO Wavfile. Now we can take a look at the Wavfile write. And we have here write a NumPy array as a Wavfile. As a parameter, it takes a file name, this is a string or an open file handle, output a Wavfile. There is the sample rate and also the data array. And also it writes a simple uncompressed Wavfile. To write multiple channels, you need to use a 2D array of shape and number of samples and number of channels. The bits per sample and PCM float will be determined by the data type. Here we have some common data types. We have the 32-bit floating point, it goes from -1 1 is a NumPy float 32. Then we have 32-bit PCM and 16-bit PCM or 8-bit PCM, and then we have the NumPy types int 32, int 16 or uint 8, and these are the minimum and the maximum values. And here we can already see that the 8-bit PCM is unsigned. And here is an example to create a 100 Hz sine wave sampled at 44.1 kHz and write it to a 16-bit PCM mono. Okay, so we've seen here how to plot the spectrogram and also to play the audio. If you want to use to play also not in Google Colab, but if you're using in your local Jupyter notebook or you're using other environments, you can use different playing methods. So let's just comment this out. So here now I'm importing IPython display as IPD. Here I'm commenting out display. So when we execute this, there will not be any playing capabilities here anymore. We can insert a new code cell and then we display IPD audio. This is the audio which is the same that we got from here, the Numpy array. We need to determine the sampling rate. By default it's using the 16 kilohertz. So when we run the cell, we have and this is now not limited to Google Colab, and we can also investigate what this is doing. Also probably it is a wrapper around this HTML5 audio control. So create an audio object. When this object is returned by an input cell or passed to the display function, it will result in audio controls being displayed in the front end, and it only works in notebooks. So you need a Jupyter notebook to use this. And you can pass the data, could be a NumPy array, a list, a Unicode string or bytes. So NumPy 1D array containing the desired waveform, 2D arrays containing waveforms for each channel, string containing a file name, byte string containing raw PCM data, or a URL pointing to a file on the web. So here for another example, generating a sound, then you're playing it back. You also can play it back from a URL. You can play it back from bytes. So it's a class, and then we have different methods. There's also an autoplay. Here we have this audio controls for the HTML, and this is taking care of all the different types of data that it supports and the multiple ways of how you can play back audio. So here we see that you can use display from the DDSP library. It's imported here from the DSP Colab Utils, and we have here the play. But you can also use the IPD, so the IPython display from the IPython library display.py. That's it for this tutorial, and in the next tutorial we are going to now look into how to compute the features. So we have here the audio features. So there should be the loudness, and there should be the fundamental frequency. So we are going to take a look how we are generating these audio features. See you next time.